Okay, I guess now it's fine. So hi everyone, I am Andrea. I will be taking on the exercises and the tutoring part for Francesco Becattini's lectures. And yeah, you can ask me also. So today I will do a couple of exercises Francesco suggested, but you can also ask whatever was not clear during the lectures of today and yesterday. Also during the school, I mean, you can find me strolling around the corridors or here in the lecture hall. So whenever you have some doubts, just come by and ask. So there are two exercises, as I was saying. The first one is more like algebra oriented. The second one has some more physics. But I will start with the one about algebra. So as you have seen in this in Francesco's lecture, we are concerned with some density operator we use to compute expectation values. And at some point, Francesco mentioned a functional of rho, which is trace rho logarithm rho minus So this is a function of the density operator, and the goal of this exercise is to find which is the density operator that makes this functional extremal, maximal. And the way to do it is similar to what one would do with in the classical statistical mechanics, so with a distribution function. The only additional difficulty is that we have to take a functional derivative of this guy with respect to some operator, which is rho. We have to put this to 0. And the only tricky part is to compute the derivative of this quantity with respect to the density operator. Also, yeah, let me just remind you, maybe this functional is obtained from the entropy. This is the entropy function. Plus, we have two Lagrange multipliers imposing some constraints on our system. For example, here we want to obtain the density operator that maximizes the entropy with a given expectation value of the operator A, which is something. You can think of this, maybe this can be the energy momentum tensor or some charge or whatever. And also we'd like the density operator to have a unitary trace because we want to interpret the entries of the density operator as probabilities. And as such, basically, there is the first step we have to do to maximize this function is, first of all, we have to realize that this is true. So the density operator is bounded basically by the identity because the eigenvalues are the probabilities to find the system in a given configuration. And therefore, we can also define an auxiliary operator, x, which is simply 1 minus rho, where 1 is the identity operator. This operator x is also bounded between 0 and 1. And we can rewrite this functional of rho in terms of a functional of x. So let me just, maybe let's write. For the moment, I will write only this first part. So x, this minus trace. Okay, this step is useful basically because a function of an operator is defined by its Taylor expansion. So it's easier to work with a logarithm of 1 minus x instead of the logarithm of rho. To compute the functional derivative, we have to compute the variation of f corresponding to a variation of rho. Basically, we have rho goes in rho plus delta rho. And this implies that x goes into x minus delta, some x plus delta x. So let's compute the variation of this f of x. Yes? This you can think of this like the eigenvalues. So the eigenvalues, this is an Hermitian operator, can be diagonalized, and the eigenvalues of the density operator are always bounded between 0 and 1. This is what I meant. Yeah, good point. Okay. So at this point, we want to find f of s plus delta x minus f of x. Okay. Basically the only tricky part in this is for the logarithm. Maybe let me write this before, or not. Let's write this before. So as I was saying, the logarithm of an operator is defined by the Taylor expansion of the operator itself. So we will have logarithm of 1 minus x is simply equal to the series from n equal to 1 to infinity of x to the n over n. This is the logarithm of this quantity. And basically, we find from this relation, we can find the derivative of the logarithm with respect to a variation in x. In fact, we can write as we have been told, basically. So let me just write delta of logarithm d 1 minus x. This is equal to, of course, the logarithm of 1 minus x plus delta x minus the logarithm of x. And from the... What? Yeah. From the above relation, we find this to be equal to the series from n equal to 1 to infinity x plus delta x n over n minus the to the n over n. Now we are interested in the first order, let's say in the variation of delta x. So this is just to infinity, and this we have x to the, this would be x to the n plus x to the n. Plus higher order. So here I am expanding this this power here. We have a leading term going to like x to the n plus the n time product of x to the n minus 1 times delta x, and then we would have, sorry, higher order in delta x. Then we have this. Sorry? Yes, I mean, I think it's irrelevant at this point. It is, but I guess they should commute.
The problem is that when you expand this, I think, you take into account the fact that x and delta x do not commute. Therefore, you have n terms, which is x, delta x, x to the n minus 2 plus x squared, delta x, x n minus 2, and so on and so forth.
Yeah. But then
everything.
Yeah, exactly. Sorry. Yeah, it's true. This is in fact not the derivative of this, but.
But we don't take trace of this exactly, right? It was multiplied by 1 minus x.
I think that you have gone a little. You have skipped some step. Which is taking the trace. I think that first, in this expansion you show, that you have to see to the x plus delta x times x plus delta x times x plus delta n times. Then expand it. Keep all the first order steps in delta x.
Yes. Yeah. Maybe this is wrong then. Oh well.
Yeah, okay, but
Yeah, at the end everything will be fine because of the trace, I guess, from here. But yeah, probably it is wrong.
Sorry, yeah, but this is very important. I think
Yeah.
otherwise, the x plus delta xn,
Mm-hmm.
you should write it as say the product of x plus delta x n times, right?
Yes. I mean, you mean n times x? I think, yeah, like
Okay.
x, delta x, and so on.
Exactly, yes.
Yeah.
X plus delta x times x plus delta x, and so on and so forth.
Okay. So this then will be, okay, x to the n minus 1 delta x plus,
Okay, yes. X delta x, x n to minus 2.
plus all the other terms. Okay, yeah, true. That's a good point. I didn't think about it.
You have x squared delta x. So
Yeah. Okay, let's write it somewhere. Okay, fine. Then again, like this term and this term cancel out, so the variation of this logarithm will be just this part here. Yeah, good point. I actually didn't think about it when I was doing the exercise. Too bad. Okay. At this point, we can now compute the derivative of that trace there. So we have f of and this is equal to the trace. Okay, we have a first part, which is just a delta x remaining from 1 minus x plus delta x minus the other term. So we have just trace of delta x logarithm 1 minus x. And then we have the second part, which is, then minus trace of yes. This part here, basically. And yeah, sorry, but I think I did something wrong then in my derivation, but okay. Yes. So at this point we would use this expansion to compute this difference, and we have the trace. The first part is and then we have the sum of this guy. Okay. So over n. But unfortunately, so yeah, no, I think I did something wrong then in my derivation. Yes, I remember. It's like. This and this?
Yeah, because I mean, in case you have an equal one, then you have like a lot of terms with x squared, delta x, 1 over x squared, for example.
So you mean there is no sum?
I mean, those terms are not originally in the initial series.
Yeah, yeah. No, I'm sorry. I think I did this exercise wrong myself.
The second and the right are not equivalent actually, the first expression.
This and this, you mean? Yeah, yeah. You're most likely right.
If you have x equals 1 and x equals 2, the substitution you don't get both. Because you get other powers of x.
No, but maybe, no, but it's, you don't get negative powers.
I think it's correct.
I think I. Yeah.
Yeah, I have to.
Please.
I think you should have simply written like some x plus delta x and times.
Yeah, but then you should take any tutor.
Okay?
Yes.
Okay. Then what you have here is that you just have to multiply all of them
Yeah, yeah, yeah.
and retaining just the first order in delta x, which means that you have x and plus. So then we have first term, the main term is x, n times.
Yeah, yeah.
Then you have x, delta x, n minus 2. Okay? Plus. You have x squared, delta x, n minus 3, and so on and so forth. Until, I mean, just shift delta x until you get, till the last term x n to minus 1 delta x.
Yep.
Okay?
Yeah, yeah.
Then you have all the delta squared, but no, that is correct. Then on the first term cancels with this, you just left with this shift. That is correct.
There is the trace, you can put the all delta x
Okay, of course,
on the
yes.
right, and
Yeah, but
then
yeah.
you can construct, you may write.
Yeah, yeah. You can reconstruct.
There are a lot of cancellations.
Yes, yes. I just don't see it right now. But yeah, the idea, of course, is that one. But I don't see how.
I mean, you
No.
can just use the simplicity.
Yeah, yeah, yeah. Okay, that's right.
But if you think that 1 minus x computes with x, so you can take that.
Yes.
Plus x over it.
Ah, yeah, sure, sure. Okay. Thank you for a good point. So the first term is okay. Yeah, then it's fine. Sorry about that. So now we can, as Professor Berardo was saying, basically we can use the cyclicity to take every term in higher powers of x to one side, commute it with 1 minus x. So we use the property x, 1 minus x equals 0. And then we have delta x isolated to one side. So we have minus trace. Here we have, for instance, I can write 1 minus x, then sum of n, x to the... basically now the thing that I was saying before applies. By doing this reordering of the x, we get n times x to the n minus 1 over n. This is not, in fact, it's n minus 2 directly, right? Yes. Yes, delta n. Sorry, let's do it like that. Let me just. Okay, so we reconstruct this. This simplifies. We have a delta x. And this is just a geometric series. So this is 1 minus x to the minus 1. So basically, this whole difference reduces to the trace of delta x, the logarithm of 1 minus x minus the trace of delta x. I mean, or minus 1. Okay. Yeah, let's say now after this, let's say, clumsy derivation, it's quite easy actually to compute the derivative of the whole thing with respect to x. basically now we have.
But maybe at this point you can also replace x with rho.
Yeah, at this point. Yeah. So since we have used this definition, basically delta x is equal to minus delta rho. So let's write it. So rho is equal, I will write it again, 1 minus x. So delta x delta rho, and this becomes the minus trace of delta rho logarithm of rho plus the trace of delta rho. I mean, there is maybe a sign, but it's not really relevant. Then at this point, f of I will do it with respect to x, f of x plus delta x minus f of x. The part with the a and with the trace are trivial. There is only a delta x remaining, basically. So this difference is just as I will still write it in x. So it's trace of delta x logarithm 1 minus x minus the trace of delta x. Then we have plus, because of the sign in delta x and the sign in rho, plus lambda 2 trace of delta x Now basically we can collect the delta x in a single trace, and we have delta x, and if we have the logarithm of 1 minus x minus 1 plus lambda 2 a plus lambda 1, and this trace is equal to 0. Writing in terms of rho, this simply becomes rho, and this is rho. And since the variation in rho is arbitrary, to get this trace equal to 0, we have to set to 0 this quantity. And this is solved by rho equals to some constant times a to the minus lambda 2a. Yes. And the constant is just the normalization constant, so it's the 1 over the partition function e to minus lambda 2a. Yes. And there's the final result. Of course, it can be generalized for more conserved charges. And that was, let's say, kind of the derivation. I'm sorry for the clumsy derivation. I didn't take into account the commutation between delta x and x. Sorry about that. Questions? No? Then, if there are no questions.
So it should be this minus sign.
Hmm?
You have delta rho, right?
Yes.
And on top you have delta x.
Yes, but
Minus sign for them.
yeah, but there is for the maximization here, it doesn't count. It's just a minus here, and it's like you're looking the variation in the different sign. What? I mean, you can put it, but it's so here this would be e to the minus 1 minus lambda 1, but this is just a constant. I called it c, and that's it. But in principle, yes, that's it. That's the correct, the complete form. Okay. So the second exercise is to basically compute, or at least guess the form, let's say, of the expectation of the. There is a. Yeah, please.
You just erased it, but you were writing the power series of the length of 1 minus x.
The sorry.
The power series of length 1 minus x.
Yes.
I mean, to my knowledge, it's minus summation.
Is.
Minus summation. I don't know. Just check.
I think it was like.
I think it's when 1 plus x then it's minus.
Yes, I think it's 1 plus x.
No, it's with minus. If you look at the lowest term, it should be negative.
So it's minus summation.
Yes.
Yeah, you
One. It was with minus.
No, no, you put the plus, but it's lower of one. Of identity minus x, it's minus the series.
yeah.
Okay. Okay, then there is also. Yes, there is.
Yeah, it explains that at some point because
So and you used all the derivation for plus summation. So maybe that was the case which was making this loop of.
I don't know. So I for sure I missed this commutation point.
Minus the series is right, because then if you take x to be a real number,
Uh-huh.
if x is a real number, between 0 and 1, lowering of 1
Yes, it's negative.
is less than what x is negative.
Yeah, so it has to be any minus.
Then it must be a minus.
Yeah.
But does not affect the final result is not affected in a sense, except that maybe the
Yeah, maybe there is a sign somewhere that I could somewhere like.
I think we should.
Yeah, maybe yeah.
Maybe we should send
I will send a revised version of this derivation. Sorry for the mistake. Yeah. Anyway, the second exercise is to basically compute the expectation value of the energy momentum tensor in the case of an homogeneous kind of equilibrium with a constant for temperature. So this would be the trace of rho T mu nu x, and here we assume as rho 1 over z e to the minus b dot p. P is the form momentum operator, is a vector operator, and b is a constant. This is important. So basically the gradients of b are 0. So we want to try to figure out how this expectation value would look like. The first thing to notice is, of course, that we don't have at our disposal many vectors along which to decompose the T mu nu, and we therefore can already expect that we will have something directed along B mu, B nu, and then we have the metric. So these are basically the ingredients we will encounter in the end. But I would like to approach this exercise in a different way using symmetries, let's say, and the transformation rules. So first of all, basically we have to realize that a tensor operator transforms in some way after a Lorentz transformation. So we have this kind of rules for T mu nu. And then the d alpha beta. So after this is the representation of a Lorentz transformation of the Hilbert space. This is the T mu nu energy momentum tensor operator at some space-time point x, and this is how it gets transformed. These are some matrix element of the Lorentz transformation. Yes. And the space-time points gets also transformed accordingly. Now, why this is important? Because using the fact that P is a vector as well as B, basically, we can try to compute this quantity in a more convenient reference frame compared to the general one. So it's also important that B squared is greater than 0. So this is a time-like vector. And we can now try to transform this this expectation value in a different reference frame. So we rewrite t mu of x as the trace of, and then we insert the identity in appropriate spots. So here we have e to the minus b dot p minus 1 lambda t mu. Again, because of the cyclicity of the trace, I've done nothing at all on our original expectation value. But now I can use these rules to transform the operators. So, okay, we'll do one step here. So first of all, by using this rule, we can transform the energy momentum tensor, and we have t mu of x equal to lambda mu alpha lambda mu beta minus 1 trace. And for the moment, let's okay. So now I've transformed the energy momentum tensor operator, and we can also transform the density operator itself. So here there are some hats missing, but okay, I guess they're also above. And to do this, again, since the exponential of an operator is defined by its Taylor expansion, one can realize that basically this transformation accounts to transforming just p. Maybe I can show this explicitly, but so we have lambda e to the minus b dot p, lambda minus 1. This is equal to lambda, the series of minus b, okay, dot p. And basically to the n. Since basically I can rewrite this product booked in using lambda lambda minus 1 inside the product. So this would be like sum n minus b times lambda b lambda minus 1 n times, basically. Over n factorial. And this is again by the same rule. This is e to the minus b lambda b lambda minus 1. Now, the full momentum is a vector operator, so it has a similar transformation rule as the energy momentum tensor, and in particular I have p lambda minus 1 is equal to lambda mu nu minus 1 and p nu. And I can use this rule to transform the density operator and write it as so basically lambda e to the minus b dot p becomes e to the minus. Here I have lambda b, or I can just let me write b mu lambda minus 1 mu nu p nu. Okay, so basically what I've done, I've moved the Lorentz transformation operator to the vector b. So now it's like I'm computing the density operator in a different frame where the for temperature vector is this lambda b. So wrapping everything up, we have found the following, that our original t mu nu of x is equal to lambda mu nu alpha beta, the trace of 1 over z, something, yeah, well, okay.
lambda minus 1 both.
Yes, sure. E to the minus lambda b p okay. So this is what we have found. And at this point, I can choose a convenient frame. So I can choose a lambda. But this was a completely general, but at this point we can choose a lambda. And we can choose lambda such that lambda b is equal to b squared times 1, 0, 0. Basically, we go to the rest frame of the fluid. So in this case, our original T mu nu is just given by this transformation. What?
No, I'm saying that lambda b equals b, not b squared.
It's like, yes.
You cannot
Yeah.
change
And then this operator becomes just the exponential of the Hamiltonian. And T alpha beta lambda x. But yeah, we can, okay. So this is what we have found. Yes. So basically we have, we are now considering this expectation value in the rest frame of our fluid. And we have changed the original question of what that expectation value looked like to what this guy looked like. So trace of e to the minus. Okay, I will just write b h t mu of x, of some point x. Now, what does this guy look like? We can tackle now this simpler problem, because now the density operator is easier. And by doing the same reasoning, we can reply the same reasoning for this, but for just rotation instead of full Lorentz transformation. Because now, by noticing that the Hamiltonian is a rotational invariant, basically this property here also implies that a rotation applied to e to the minus b Hamiltonian is equal to e to the minus b Hamiltonian, because the Hamiltonian is rotational invariant. So we find that this is equal to some rotation minus 1 mu alpha, rotation minus 1 mu beta, trace of minus b h t alpha beta. And here we will have the rotated spacetime, but we can assume that spacetime is rotational invariant. I mean that spacetime is homogeneous, so we can just put x here. And we obtain this equation. And from here, we can basically see what the component of the energy momentum tensor look like. Let me call this T mu nu 0. And we have found that T mu nu 0 of x is equal to rotation minus 1 mu alpha.
Yeah, sorry, can I make a comment?
Please.
You do not assume really that the space is rotational invariant. So the x should be kept there. The only problem is, the key point is the following: is that this operator is also invariant by translation. Therefore, the mean values do not depend on x. And you can choose a special point, which is x equals 0.
Yes, that's also true.
This is the only case where x is equal to x.
Yeah, Yeah, okay.
Because otherwise you cannot replace
Rx equal.
Rx with X, yes.
Okay.
Sorry, but you should, yeah.
Okay, sorry for being.
That is to point it out. So that, and then you can choose X equals 0, and
Mm-hmm.
that's it.
That's true. That's true. Then yes, let's choose X equals 0. But then everything now should work fine, because a rotation in the Lorentz group look like this. So we have 1, 0, 0, 0, and then a proper rotation, the element of SO3. And at this point we can realize like the space component of T mu nu are such that Tej 0 at the point 0 is equal to RIL J S TLS 0, where I, J, and LS go from 1 to 3. And the only matrix that is left invariant by this means that the space part of the energy momentum tensor is left invariant by rotations, and it means that Tij must be proportional to the identity. And we can call this Tij equals pressure identity. And also we have Ti0 is equal to a rotation IL yeah, then we have, oh wait. Yes, rotation. I mean, this means that this is equal to 0, okay. We have this other relation, which also means that Ti0 is equal to 0. Yes, it's equal to 0. And finally, since the 0, 0 element of the rotations is just 1, we get not much information on T0, 0. And we call this the energy density. So basically, this means that in this rest frame, our T mu nu looks like this: epsilon P, and yeah, this is 0. And we can write this using like the this 4 vector there, so 1, 0, 0, 0, and the metric. Let me write it somewhere, maybe here. No, maybe not here, maybe in this. So, yeah. Would be equal to epsilon. Yes. This would be basically epsilon plus P. Let me call this U mu 0, U nu 0. No, sorry. It's epsilon. Let me write it. This would be this matrix represented using the 4 vectors of the 4 velocity. Here U0 is just 1, 0. And by the definition of lambda, basically if we apply from this formula, we have T mu nu of x equal lambda minus 1 mu alpha lambda T0 alpha beta. And we have from that equation, we have that lambda minus 1 mu alpha to U0 is just equal to U. mu. Because b here, maybe I should have written this, b here is just some b times u mu. And finally, t mu nu x is equal to epsilon. And that's it. Okay. So this is the form of the ideal energy momentum tensor in an homogeneous equilibrium. Again, it's important that there are no gradient. The b mu has no gradients. Otherwise, we can have different vectors along which to decompose the energy momentum tensor. For example, the vorticity or the acceleration. Or but yes, this is the ideal result. So, if you have any questions.
Another point to be stressed here that if you, with this operator, e to the minus b dot p t mu x, then t mu does not depend on x at all.
Yeah, that's true. That's true.
You have any bias by translation in
True. True.
all of them.
Yeah. It's right. It's right. Okay. So that will be it, and we are perfectly on time. So yeah, again, sorry for the clumsy derivation before. I will provide you with the correct answer for the first exercise. And if you have any question also in what follows, please ask. Yeah.